Okay. So we will do the Lewis structure of HF as the first molecule. And the first step is to count the total number of valence electrons. For this, you need your periodic table. And remember how the main group elements, the A groups, the group number is equal to the number of valence electrons, right? So that's how we will get the number of valence electrons for each element. So hydrogen in group 1A has 1 valence electrons. And there is only 1 in the formula. And then F, fluorine, has, so tell me, how many valence electrons for fluorine? So fluorine is in group, oh no, not the ion that it makes. I want the number of valence electrons on fluorine. And so the group number gives you the number of valence electrons. So because fluorine is in group 7A, it has 7 valence electrons. And yes, it likes to gain 1 electron to become a -1 ion. But the reason is that it's because it has 7 valence electrons and it needs only 1 more to be surrounded by 8. And they all want octet. Remember how all atoms want octet, which means 8 valence electrons around them. And so right now it has 7 and hydrogen 1. So the total will be 8 electrons, right? So that's the number of electrons we will need to distribute. Next, you want to position your 2 atoms. And here, you know, just H and F, there's nothing complicated about that. You just place H and then let's keep some room for F. Okay? Oh, okay, I have to separate them. Okay, I'll remove that completely because, okay, H and then F. So the first step is to draw the bond between them. And so you draw a single line between H and F, and that will represent 2 electrons. So then out of your total, you want to subtract. So we want to do 8 minus 2 electrons from the bond, you know, the single bond, is equal to 6 electrons left. 6 electrons left. So those electrons, now you will distribute them as lone pairs, and you, so normally you start with the outside atoms, but here we have only 2 atoms, so it doesn't matter. However, hydrogen is an exception to the octet rule. Hydrogen only wants 2 electrons around it. So if you look at hydrogen in the periodic table, it's in the upper left corner. Atomic number 1 has 1 proton and 1 electron. And it likes to be like helium. And helium on the other side, on the upper right corner of the periodic table, it's in group 8A, but helium is an exception among the noble gases. Helium, atomic number 2, has only 2 protons and 2 electrons. And it's very stable like that. And the reason why it has only 2 protons, 2 electrons, it's because the first shell, because we are in period 1, the first shell is only made of 1 s orbital. 1 subshell and 1 orbital. So the 1s orbital, and the 1s orbital can contain only 2 electrons maximum. So that's why this is a complete shell when you have 2 electrons in the first shell. And so because of that, helium is very stable, because whenever you complete a shell, it makes the atoms very stable. So helium is very stable, and hydrogen will want to be like helium and have 2 electrons around it. And right now, when it has a single bond with F, it is already surrounded by 2 electrons, because that line here represents 2 electrons that are shared, right? They are shared between H and F. because you know, non-metals and covalent compounds share electrons. It's very different from ionic compound. And here, hydrogen has a single bond, and it's already having what we call a duet, which means 2 electrons, and it's stable. So never, ever do a lone pair on hydrogen. So those 6 electrons left will have to go around fluorine. And so let me draw them. 1, 2. Yeah, I have to make them big enough. They look awful, but let me redo this one. Oh boy, don't know what I did, but okay, it really looks awful, but it's very hard to draw on this. Okay, 6 dots around F. I'm sorry, it looks bad, but I don't know how to do this otherwise. So when you're doing this, you have used 6 electrons. So 6 minus 6 that you used in lone pairs around fluorine. And that's 0 electrons left. And that's what we want to arrive at. We want to have used all our electrons. So 0 electrons left, and let me just write it like this to gain room. Okay, so 0 electrons left. We have used all our electrons. And so the way you want to check that your Lewis structure is correct is by counting the total number of valence electrons that you have on your structure and verifying that each atom has a duet or an octet for most of the elements. And so here, hydrogen has a single bond here, which means it has a duet, it's happy. Fluorine has 6 electrons around it, plus the 2 from the single bond, that's 8 electrons, and that's an octet, and it's happy. And then let's verify we have 8 valence electrons in total, and here we have 6 around fluorine, plus 2 in the single bond, that's 8 in total. So what you want to do is, you know, check that we have 8 electrons in total, and check that we have an octet and duet. You know, I can write for octet here and duet here. Duet. Okay. So that was a easy one just to show you the process, right? So let's do SiH3 Cl. And again, the 3 here should be a subscript, and I cannot do that. So take it as a subscript, which means there is 3 hydrogens. 1 Si is silicon and 1 chlorine. Okay, so count the total number of valence electrons. So here, Si, can you tell me what is the total, you know, the number of valence electrons that silicon has? From the periodic table, look at the group number, and that tells you the number of valence electrons. So go ahead in the chat and tell me that. How many for silicon? Yes, it's 4 because it's like carbon, it's in group 4A. And notice how silicon is a metalloid because, you know, it's a metalloid, but it makes it makes covalent bond, right? When it binds with non-metals. And here hydrogen is also a non-metal, even though it's in group 1A among the alkali metals. Remember how it is an exception, it's a non-metal with 1 valence electrons. And we have 3 of them. So you need to multiply by 3, right? Next, we have chlorine. Chlorine is in group. So tell me, what is the number of valence electrons for chlorine? Yes, 7. So we have a total of, let's see, 4 plus 3, it's 7. 7 plus 7 is 14. So 14 electrons. And the way I will write electron is just E with the negative charge, you know, that means electrons there, okay? So that's our total number of valence electrons. Let's position the atoms now. So typically, you want to position the most metallic element in the center. Another way to see it is that the most metallic element is also usually the first one in the formula. And so here, silicon is the first one in the formula. You see that silicon compared to chlorine is more metallic because silicon is a metalloid, chlorine is a non-metal, hydrogen is a non-metal. So out of these 4, silicon is definitely the more metallic. And so you would place it in the center. And it's really behaving like carbon, and carbon is always in the center. Then you place, you know, around an atom, there are typically 4 sides. And so you place the other atoms on the 4 sides around the central atom, which is silicon here. So let's place hydrogen on top, oops, above, I said. Let's do that again. Here, hydrogen, another one below. Oops, hydrogen, another one on the left side. And then chlorine on the right side, right? They should be all at the same distance, but it's a bit hard to position things here. Okay, I can move that. Okay, good. So silicon is surrounded by the 3 hydrogens and the chlorine. So then the first step now is to distribute the electrons. And for this, we will do single bonds between the atoms, you know, between the central atom and the hydrogens and the silicon and the chlorine. And then you want to remove the number of electrons you used from your total. So you do 14 minus, and here we've used 4 single bonds. They each have 2 electrons, right? Because a line represents 2 electrons. So 4 times 2 is 8. So we remove 8 to the total, and that's 6 left, electrons left at that point. The next step is to distribute the lone pairs to complete the octet of the outside atoms first. And here, I don't record. How come? Oh, wait, hold on. Yes, I do record. I'm sorry. Got scared for a minute. Yes, so the next step is to distribute the lone pairs to complete the octet of the outside atoms. And so the outside atoms here are the hydrogens and the chlorine. But as I said earlier, hydrogen is an exception and it wants a duet. So they all want duets. And so I will write this here, duets. No, didn't write duets. So we want duets for the hydrogens, right? And right now they all have a duet. When they have a single bond, they have 2 electrons around them, and that's what they want. So never ever do a lone pair on nitrogen. Hydrogen will always, end your structure. It's like an atom that can make only a single bond, so you cannot build on it, right? So that's why it's always on the outside. So then the lone pairs will have to go on the chlorine. And I have 6 electrons left, and that's exactly what I need to make an octet for chlorine, because right now it has 2 electrons from the bond here. So let's give 1, 2, 3, 4, 5, and 6. Okay, they are not all the same size, but that's better. I'm improving. So we have positioned our 6 electrons left here. 6 minus 6 equals 0 electrons left. Okay, and so now we have used all the electrons that were available to distribute. Chlorine has an octet, and now let's verify that silicon has an octet. And you can see that when you have 4 single bonds, 2 electrons each, that's 8 electrons around silicon. So they both have an octet too. So octets, let me write that, octets. No, octets. And so we can see that we have duets for this hydrogen, that hydrogen, this hydrogen, and we have an octet for the chlorine, because 6 from the lone pairs plus 2 here, it's 8. And the silicon has also 8 around it. So that makes it happy. So we have our octets and duets, and now let's verify that we have a total of 14 electrons each. So we have 4 bonds. So let's do this below. So 4 bonds, so times 2 electrons each, plus 4 bonds times 2 electrons each, that's 8, plus 3 lone pairs, times 2 electrons each. So 2 times 4 is 8, plus 2 times 3 is 6, that's 14. So we have our 14 electrons in total. So we check that this is done too. Okay? So always check that. If you check that, then you are sure you will have a correct Lewis structure. So let's do NCl3. Do you follow? Are you okay? Okay, so let's do NCl3. So again, here, the 3 should be a subscript for chlorine. I cannot make it as a subscript, so, but take it as a subscript. So it's NCl3. So let's count the total number of valence electrons. So nitrogen, brings, so how many valence electrons from nitrogen? Mm. 5, yes. Try to move this, but no. Okay. Shouldn't have get. Sorry, I have trouble. So tell me how many valence electrons in don't know how to do this. Okay, finally. So 5 electrons from nitrogen, then chlorine. How many from chlorines? And we had chlorine earlier, and chlorine is in group 7A. So it brings 7 valence electrons, and there are 3 of them, so times 3, right? And so the total is, so you do 3 times 7, 21 plus 5 is 26 electrons in total. Okay, so that's the number of electrons we will need to distribute. So next you want to position your atoms. And so here, again, NCl3. So typically molecules try to be symmetrical, or, and again here, N is first in the formula. And so it will be the one in the center. And chlorine, because they already have 7 valence electrons, they only need 1 more electron. And by doing a single bond, they will get that electron. And so typically they are on the outside, because you cannot build on an atom that can only do a single bond. So we know that nitrogen will be in the center. And then it will be surrounded by the chlorines on 3 sides. Okay. Right. So the first step is to draw the lines to do the single bonds between your atoms. And so let's start by doing this. So between the 3 chlorine and the N. And so you want to count the number of electrons left after that. And so you do your total, 26 minus. And here we've used 3 single bonds times 2 electrons each. So we've used 6 electrons. So that's 20 electrons left that we can still use and distribute. So the next step is to use lone pairs to complete the octet of the outside atoms first. And so here the outside atoms are the chlorines. So we will want to do lone pairs on the chlorines, and each chlorine has a single bond. A single bond means 2 electrons each for each of them at this time. And so we want to give them 6 electrons so that they get an octet, right? So by doing 3 lone pairs on each chlorine, they will each get an octet. And 3 lone pairs times 2 electrons, that's 6 electrons per chlorine, times 3 chlorines, that's 18, right? So we will have enough to do that. So let's do this. So 1, 2, 3, 4, 5, and 6 for 1. 1, 2, 3, 4, 6 for the second, and 1, 2, 6. Okay, so I've used so out of 20 we have used 3 lone pairs per chlorine times 2 electrons each. That's 6 electrons per chlorine times 3, so that's 18, right? And then we have 2 electrons left. So the chlorines have their octet, right? If we type here octets, Okay, so the chlorines have their octet, 1, 2, and 3. The nitrogen doesn't have an octet because there is 2, 4, 6 electrons around it right now. So we will give those 2 electrons to the nitrogen, and it will have a lone pair here on top. And that will use all the electrons, and that will give an octet to nitrogen. So 2 minus 2, 0 electrons left. So that uses all the electrons, and that gives an octet to nitrogen, right? 6 here from the single bonds plus 2 here, it's an octet for nitrogen. So looks like all atoms have an octet. And now let's verify that we have 26 electrons in total. So let's count that. So we have 3 single bonds, 3 bonds times 2 electrons each. Plus, okay, we have 3 lone, well, so let's count the lone pairs. So 3 on 1 chlorine plus 3, it's 6, plus another 3, it's 9, 10, right? 10 lone pairs. Oops, lone pairs, so times 2 electrons each. So 10 times 2 is 20, plus 2 times 3 is 6, that's 26. That's exactly what we need. Okay, so the total number of valence electrons, sorry, total is correct. Hold on, I'm gonna stop. Okay, ONCl. So let's count the total number of valence electrons. It's a step that is important. So oxygen, remember how the group number tells you the number of valence electrons that each atom brings. So here oxygen is in group, so tell me that. How many valence electrons from oxygen? Yes. Oxygen is in group 6A, it brings 6 valence electrons. We have only 1 oxygen. Nitrogen in group, and so we've seen that one before, in group 5A, right? So nitrogen brings 5. And then chlorine in group 7A brings 7. And it's 1 of each. So we just calculate the total here. And it's 18, right? Tell me if it's wrong. 18 electrons in total, right? 7 plus 5 is 12 plus 6. Yeah. So we have 18 electrons in this structure that we will be able to distribute. Let me make this smaller. And I will do the structure here. So which one will be the central atom? This molecule is kind of weird, but the order shown in the formula is the order you want to have for the molecule. So you will want to put the nitrogen in the center. Nitrogen. Then let's give oxygen to the, no, I have to click that first, oxygen. And then chlorine on the other side, right? So we will all put them in one line. They are all, sorry. Okay. So once you've placed them, you know, according to the arrangement that should work, then you do the single bonds. So let's distribute electrons and start with single bonds, and you start with the atoms from the outside and join them to the central atom and do single bonds. Every line here represents 2 electrons, and so we want to remove that from the total. So let's calculate that here. So we have 18 electrons in total minus, so 2 single bonds times 2 electrons, it's 4. So we've used 4 electrons, and that's 14 electrons left. Electrons left to distribute, right? So the next step is to distribute lone pairs on the atoms around the outside, on the periphery, which means not the central atom, but the others around. And you want to complete their octet by giving them lone pairs to complete their octet. And so right now, oxygen has 2 electrons from the single bond. And so you will want to give it 3 lone pairs, because those 2 electrons plus 6, it's going to be 8 around the oxygen. So let's distribute those lone pairs on oxygen. And that's 1. Oops. Okay. 2, 3, 4. 5, 6. Oxygen now has 6. Okay, 6 valence, 6 lone pair. Sorry, 6 electrons from lone pairs, plus those 2 electrons from the single bond. That's an octet for oxygen, right? Octet. Oxygen has an octet here. Let's do, and we've used only 6 minus 14. Looks like we have enough to give 6 to the chlorine. So let's do those lone pairs on the chlorine. 1, 2, 3, 4, 6. So 6 electrons around chlorine, plus the 2 from the single bond. That's an octet for chlorine, right? And so let's count to make sure we have enough electrons left, or that we haven't used everything. So we had 14 left, minus we've used 6 around oxygen, plus 6 around chlorine, that's 12. So 14 minus 12 is 2. So we have 2 electrons left, right? So those 2 electrons left, now we need to use them to give an octet to the nitrogen. But we have only 2 here, so let's place those 2, and then we have to stop because we cannot put more than there is electrons available. 1 and 2. So we've used our 2 electrons here left. 2 minus 2 equal 0. 0 electrons left. So we've used all our electrons, and if you look at nitrogen, it doesn't have an octet because nitrogen has a single bond on the left, that's 2, plus a single bond on the right, that's 2 more, that's 4 electrons, plus those 2 on as a lone pair, that's 6 electrons around nitrogen. So 6 electrons is not 8, so it's missing 2 electrons. So the thing is, we have used all the electrons that were available, so you cannot bring more, right? You cannot bring more. So when that happens, you have to distribute lone pairs and share them. And so here, the oxygen could share, or the chlorine can share, right? Both of them. But if you think about the common bonding patterns, and I just said that earlier, chlorine is an halogen from group 7A, has 7 valence electrons, and it likes to gain only 1 electron, and so make a single bond, because this way it has 8 valence electrons around it. So chlorine is not inclined to make a double bond. It typically doesn't make double bond. Now, if we look at oxygen, oxygen in group 6A has 6 valence electrons. Usually it likes to make 2 bonds. It likes to make 2 bonds to gain 2 electrons from, sharing electrons. So, well, yeah, that what I'm saying here is that if you look at the common bonding patterns, oxygen likes to make 2 bonds. And so it will be oxygen who will share. Let me show that we will do this sharing here. And so we will give that lone pair, and let me make it red. Or can it be red? No, I don't know. Oh, I had to do it before. Hold on. Okay, so let's share this one. And this will be shared like this. I'm trying to find an arrow that shows that. Okay, I will use this red. Okay, so we will need to redraw our structure because we don't want to get confused. So let me redo it here. N. O. Cl. Let's do our single bonds again. Hold on, I need to move this up. Well, it doesn't need to be red. So oxygen will have 2 lone pairs left, only out of 3. And that lone pair here will now form a double bond with nitrogen. Okay, so that's what it becomes after they share, the oxygen shares its a lone pair. So we have a double bond now. And if we think about the common bonding patterns, it's natural for oxygen to have a double bond. And it's also a common pattern for nitrogen to make 3 bonds and have a lone pair. And it's common for chlorine to have 3 lone pairs and 1 single bond. So they are all, binding in their common ways. So now we have an octet on nitrogen. If you look, those double bonds, they have 4 electrons. There is 4 electrons in there, plus 2 electrons from the single bond, plus 2 electrons from the lone pair. So now we have an octet around nitrogen, right? And we still have an octet around that chlorine. 6 plus 2 here, it's 8. And oxygen, so there is 4 electrons in the double bond, right? Each line is 2 electrons, so 4 plus 4 from those 2 lone pairs. So they each, so oxygen still has an octet. And now we need to count the number of total valence electrons and make sure we have 18. So let's count that by counting the number of bonds. So we have 1 double bond and a single bond. So let's say 3 bonds times 2 electrons plus, so let's count the lone pairs. 1, 2, 3, 4, 5, 6. we have 6 lone pairs times 2 electrons each. So 6 lone pairs times 2 electrons each, it's 12, plus 3 times 2 is 6, 12 plus 6 is 18. So we have 18 electrons total. And that's the correct number. So we can check here that it is correct. And so that's the structure for ONCl. All right. So let's do more last one here. Unless you are ready to go, but I missed. And let me draw a line here to show that this is from different things here, from here, and then another one from here. Oops. Oh, stop. Like this, okay. Okay. The formula is CH3, and again the 3 here is a subscript COOH, and I will tell you how to position the atoms. CH3 COOH. This is actually acetic acid. And so let's count the total number of valence electrons we have, and we'll do it here to make sure we have enough room. So carbon, we have 2 carbons, right? 2 carbons, and they each bring, so tell me again, how many electrons from the carbons? Remember, yes, the number of valence electrons is equal to the group number. And here carbon is in group 4A, so carbon, each carbon brings 4, but we have 2 carbons, so we multiply by 2. Hydrogen. Hydrogen brings 1. And we have how many hydrogens? So be careful, the formula is written in a certain way. If you continue with chemistry 131, you will learn to recognize what this means. Yes, 1 times, and there is 4 hydrogens, right? Remember how that 3 here is a subscript for hydrogen. And the last hydrogen here, you need to add that to it. So it's 4 hydrogens, right? Be careful. And so we've counted the carbons, the hydrogens, and we have the oxygens. Oxygen, group 6A has 6 valence electrons, and we have 2 oxygens. So the total number of valence electrons here is, so 2 times 6 is 12. 12, and then we have 3 times 4, basically. So another 12, so it should be 24. 24 electrons total, right? So let's do the structure somewhere here. Yeah, so carbon, I told you, is an element that it will always be a central atom, always position itself in the center. We already discussed the fact that hydrogen, because it wants a duet only, 2 electrons, it needs a single bond only. You cannot build on it, so it will always be on the outside. So never put hydrogen in the center. So carbon will be in the center. And then the oxygen, I will show you how you are supposed to put them. I know you cannot guess, I have to tell you that. So we will have C here, 1C, 1C. And then let's give that C, okay, I have to yeah, I'll put one in hydrogen here. One hydrogen, another hydrogen here, and another on the bottom of that. Okay, I'll position them afterwards. Carbon, the carbons are bonded together typically. You will want to put them together. And then you will give the oxygens, the two oxygens to one carbon, right? They are going to the same carbon. So oxygen, another oxygen on that side. And one of the oxygen will have the hydrogen. That's why that hydrogen is not, part of the three over there. So let me try to rearrange this more neatly. So this should be like that. Oops. Carbon. That oxygen will be bonded to carbon. This oxygen to carbon, and that hydrogen to the oxygen. Right? You see what I mean? So that's how it is. That COOH is what we call a carboxylic acid function, and it's the two oxygens are bonded to the carbon, and then the hydrogen is bonded to one of the oxygen. Okay, so let's distribute single bonds, and we will bind our two carbons, right? Then that left carbon will get all the other hydrogens, and the other carbon will get the two oxygens, and the last hydrogen will bind to the oxygen. So let's count the number of atoms we've used. We started with 24 minus, we have 1, 2, 3, 4, 5, 6, 7 bonds, 7 bonds times 2 electrons. So that's 14 electrons. That's 10 electrons left. Right? So we've used 14 electrons by doing those single bonds. We have 10 electrons left. So the next step is to distribute those 10 electrons left into lone pairs to complete octet of outside atoms. Here we have a lot of hydrogens, and as we said earlier, hydrogen is happy with a single bond. It wants a duet, 2 electrons only, and all hydrogens here, and I can write that duets. Hydrogens, they want duets, and they each have their duet already. Here, there, and there. So we don't bother with the hydrogens anymore. They are happy, and you never ever give a lone pair to an hydrogen. So then the outside atoms are the oxygen now, right? The carbons are considered central. So we'll distribute those lone pairs to the oxygen. And we have 10 electrons left. So let's give 6 to that oxygen here, the bottom one. And so let's do 1, 2, 3, 4, 5, 6. We've used 6 electrons, so 10 minus 6, we still have 4. Well, looks like it's exactly what we need, because here, if you look at this oxygen, it has 2 single bonds, which means 4 electrons around it right now, and it wants 8. So it needs 4 more. So you can give it 4 more. Here, 1, 2, 3, 4. So we can deduct the fact that we have used our 10 electrons here, right? 6 on one oxygen and 4 on the other. So that's 10 equals 0 electrons left. So we've used all our electrons, so we cannot bring any more. The next step is, So let me write that we need octets here. Octets. Octets. And I want to show that we have octets for our that oxygen here. And this has an octet too, but I'll not put the fact that we have an octet yet, because here I see that the first carbon on the left has an octet because 4 single bonds makes it an octet, right? 4 times 2 electrons each, it's 8 around that C. That oxygen has a lone pair because 4 from the 2 single bonds plus 4 from the lone pairs, that's 8. This oxygen is happy too. It has 6 plus 2 here is 8. But that carbon has only 6, right? 3 single bonds make 6 electrons around it, and it's missing 2. However, we have no more electrons available. So that means one of the oxygen will have to share a lone pair. And when you have the choice like that, you need to think about the common bonding patterns. And I told you earlier that oxygen likes to make two bonds. 2 bonds. And here, this oxygen only makes 1. So this one will be more willing to share a lone pair, because you don't want this one to share a lone pair, because if it does, that means it will have a double bond on the left and a single bond on the right. That will mean 3 bonds for the oxygen, and that's not typical of oxygen. So you don't want this one to share. You want that bottom oxygen to share. And if I select this, I will show that I will get a lone pair from this. And then that. So that lone pair will be shared with the carbon. Let's see if I can select everything instead of, can I select that? And copy and paste. I'm trying something. I don't know if it's possible. Maybe not. No, it looks like I cannot copy and paste. If I try again. I'm doing the traditional Control-C, Control-V, but that doesn't work. So I have to redraw everything. Instead of redrawing everything, I will erase. But you saw, oops, oh, no, not that. Undo. I have to be careful with my eraser. Okay, I'm erasing. Oh, I'm erasing the lone. I need to erase the lone pair, or you know what? I will erase the one here. Okay. And now instead of having 3 lone pairs, we will have a double bond here. Maybe I should put this the same color, right? Oh. Okay, so now we have a double bond between the bottom oxygen and the carbon. And so this way, carbon has 2, 4, 6, 8 electrons around it. And the oxygen still has 4 from the double bond plus 4 from the lone pairs, that's 8. So they each have an octet. And so they each have an octet, okay? So let's count the total number of valence electrons that we have in the structure to verify that we have indeed 24 electrons, because we already checked that we have duets and octets for all other atoms. Oh, by the way, this one also is having an octet. So let's count. We have 1, 2, 3, 4, 5, 6, 7, 8 bonds. You know, I'm not taking into account that it's double bonds. So 8 bonds times 2 electrons each. Plus lone pairs, we have 1, 2, 3, 4 lone pairs. 4 lone pairs times 2 electrons each. And that's, so 2 times 8 is 16 plus 4 is 20, 24. That's 24. And that's what we needed. Okay, so that's correct. So we have the correct number of valence electrons in the structure. And that's acetic acid. It has a double bond.